we have this interesting problem. We have a bar. This is a steel bar, steel rod. And as you can see at A, this is a fixed end. And at C, point C, there is a force applied to the right for 20 kilonewton. And very interestingly, we have an opposite war at B prime. And this rod has a gap between the end of the rod and this wall about at 0.2 millimeter. And the rod, and then determine the reactions at A, and neglect the size of the color at C. So then you can neglect that this, the color. So then you can assume that this is like a constant cross section, and takes, the Young's modulus of steel is a 200 gigapascal. This is an interesting problem, right? So I will switch to the my whiteboard. Okay. So the first step is to draw the free body diagram, and I actually have a free body diagram here. So this is the the problem shown in the question, and you can think that this is combination of two cases. Due to the force, it will elongate, right? So then we're gonna have delta P is this. But this, as you can see, that there is no wall, right? On at the right end. So then this is like a purely free end rod, right? So we have delta P here. And then we also have another case, FB. So then this is actually, you can think that this is a reaction force FB. And if we apply this reaction force, and then it will compress. Oops. And the delta B, so that it will compress, so that it will shrink. So this original case can be combination of these two cases using superposition, principle of superposition. And if the this force is large enough, then it will touch. So then delta P plus delta B should be what? should be equal to what? 0.2. 0.2, correct. Because we have 0.2 millimeter, right? So the only difference from the previous, example in my lecture note was previously was a fixed, but now we have a 0.2 millimeter gap. And if you add delta P plus delta B, we're gonna have a 0.2 millimeter. And this is a fun example. Okay. So in this case, we have two reaction forces, we have a one equilibrium, so that we could not solve, but having this compatibility equation, we can solve the problem. The first step is statical equilibrium. We know that. Right? We have, from the statics, we have FA, which is, I'm actually setting this, to the right. I actually made it positive. So then we have to the right, negative is equal to 0. And do you see something strange? One thing I want to really emphasize here, we're gonna use two things, right? This is a statics. And if you remember the statics, the force direction is, I said it, to the right is positive. That means to the left is negative, right? But in the mechanics of material, just 5 minutes ago, I said that compression is negative and tension is positive. Do you see the two different sign convention here? So very important thing is when you deal with statics, either you can set it, to the right is a positive or to the left is a positive, as long as you are consistent. But when you deal with the deformation, shrinkage is negative, the elongation is positive, okay? And this is a statical equilibrium. So, we don't deal with the deformation, right? So then we just use a sign convention as I said. Make sense? That is very important. And this is equation 1. Second is, because this is a statically indeterminate, so Amir asked, does it so happen that the deformation convention match the direction convention? Not necessarily. It is always the same. Because when you think about the compression or tension, right? Okay, I will draw it here. If you think about the tension, for example, to have a tension, you have to have a two different direction force, right? Compression is the same. So in statics, this is a positive and this is a negative. But if you think about deformation, this entire thing as a negative. Okay? So when you think about deformation, compression or tensions are important, determines which sign you have to use. In statics, which is static means not moving. When you consider that statical equilibrium, you want to consistent to the whatever you made your sign convention. Okay, so did I answer your question, Amir? Yeah, this is very important. So that's a very good question. The second thing is, because this is a statical indeterminate, so we need a compatibility. Which is so if we elongate this way, this will be what? 0.02, which is a gap size. And then this is delta P and delta B. I made it negative, right? Because this will be compression. And I made this positive because this is elongation. Very important. So then our goal is to convert delta P and delta B to FA and FB. Again, our goal is to determine the reaction at A, FA, right? So then our goal is to determine this value. Of course, you will see that we can also determine the FB, right? So we have delta P and delta B. So what we need is, deformation formula. So what was the deformation formula? Delta is equal to anyone on the numerator? We will need force P, right? And length L. Jacob, thank you. PL over, oops. EA. So then we're going to use this formula. And you can see that what we need is we need to convert delta to force, which is FA and FB, right? So then we will get the secondary equation. So delta P is P LEC over AE. A is the rod cross-section area, pi 0.005 square, and 200 gigapascal into the 9 is equal to 0.5093 10 to the minus 3. Of course, this will be millimeter. Oh, this is meter, right? And delta B is, now I'm solving for the second. George, 0.4 is this length. Yep, that's correct. P, no, not P. We're solving for FB, right? FB, L, AB. One thing that you need to make, you need to be careful is the length. So then this length will be, entire length will be our, under our consideration. So then LAB is a right length to use for FB. And AE is the same because we ignore the color. So then FB is something we need to calculate. This is 1.2 pi 0.005 square 200 gigapascal 76.3944 10 to the minus 9 FB meter. Why did you use 0.8? Where is the 0.8? Jacob, where is 0.8? I don't length CV. Ah, that's what I meant. Because answer is this. Because the second one is this one, right? And then when you press that, what is the length? Because this is the end of the rod, and then this is a fixed end. So the entire length will be the under consideration. Did I answer your question, Jacob? Okay, good. And Gabriel, why don't we include FA in the second? In fact, that I included here, and then I didn't show here. So yeah, to be accurate, to be accurate, this should be this, and this should be this. But the reason that I didn't include FB here and FP here is for the, the compatibility equation. I don't use this, equilibrium condition of this two. I only use the equilibrium condition for this. Okay, so good. So then, oh, so this is, I'm going to call this equation 2. So then we have two equations, two unknowns. We can solve this problem. So then from what am I doing? From equation 1 and 2, 0.0002 equal to 0.5093 10 to the minus 3 minus 76.3944 10 to the minus 9 FB, and we had one more equation, right? So then FB can be, now we have only one variable, so we can solve it. Kilonewton. Going. And 4 equation 1 FA is 16.0 kilonewton. So Jenny asked, okay, where did the 4.5 come from, or you just skip this? What I did is I wrote here, I'm combining this equation and this equation and plug in these values. Do you see that, Jenny? So again, what we did is we have a delta P, right? And here, delta P, we have this number, constant. Delta B is function of FB. So if you plug that in here, then you can determine FB, right? Because FB is the only unknown. So we have constant FB, so we can solve this one. You're right, because I actually, I meant that using here, so then you're correct. So I didn't use equation 1. Yep, thanks for that. Any other question about this? So this is an interesting problem, but also this is the important problem in chapter 4. I will review in my exam 1 review session, but as you can see in the solutions, when I ask this statically indeterminate problem, in fact that I ask everything. So I asked how you can construct the statical equilibrium equation, and also I asked about the deformation and how you use the deformation equation, convert that to the the compatibility equation. So if I ask a statically indeterminate problem, in fact, I ask all the materials in chapter 4. That's why I'm saying that you will definitely see the statically indeterminate problem in the exam 1. So, this is an example, and then you also have an example problem in the textbook. And also I included the, statically indeterminate problems in the homework. So then I think you will have plenty of, chances to practice this.